So Specutils is the underlayer for a lot of the spectral analysis that you're going to be using for JWST. Specutils is a project that's come out of the AstroPi project. It's part of a wider spectroscopic ecosystem that is outlined in more detail in this link I've got here, this AstroPi proposal for enhancement 13. We won't dwell on that right now. The key point is there's several things for general use that you might be interested in, or even for non-JWST data, but it's meant to be a layer that projects like JWST can build off of, and that's why we're focusing on it today. It's the sort of both the data structures, the things you use to represent spectra in Python, and the sort of basic analysis tools like line measurements and the like. All of that lives in Specutils, and even though there's other packages like SpecReduce and then the JDAVIS package you'll hear more from in the next two parts of this webinar, this one is focused on Specutils because it's the sort of the first layer in the whole situation. I'm going to start first by just running some imports. If you're not sure how imports work, don't worry too much about it. We're pulling in several packages from the outside world, like NumPy for basic array math, the units package from AstroPi to represent numbers with attached units, the fits subpackage from AstroPi, which is used to load fits files, and then several things from Specutils. Right, all of these things are from Specutils imports something. And that's what we'll be using later on in the notebook to actually do some of these spectral analysis tasks. And then the second line here is all about plotting tools and this quantity support thing. If you want to know more about it, you can ask me about it in Slack, but except for now that it's just a magic thing you have to do to get plotting to work well with these quantity objects and spectra. So with that in mind, let me spend just a little bit of time talking about the underlying data structures you're going to be interacting with using Specutils. So Specutils has several different objects for representing spectra. I'm really only going to focus on one for today because there's sort of the simplest or most straightforward one to understand is this one called Spectrum 1D. I'm showing the other ones primarily because if you end up in a more complicated data structure like a data cube that you have to sort of roll your own, you might need to know about the existence of these data structures. You can look on your own in the documentation if you want to later, if that strikes your interest. But the core data structure we're going to be working with right now is just this one called Spectrum 1D. So the main point of Spectrum 1D is to provide a Python object that lets you keep all of the information about a particular spectrum in one place, essentially. Makes it so you don't have to carry around the wavelength and the flux and the uncertainty as three completely separate objects in Python. The Spectrum 1D object is just one thing, one object that you can carry around as an individual variable in Python. So that means it has to have all of the things associated with a spectrum. For Spectrum 1D, that basically means a spectral axis, which is basically an array with associated units that need to be spectral units, and a flux. That's sort of the minimal two things you need for a spectrum. You can think of it as the x-axis and the y-axis. So the flux axis then has to match the spectral axis, but has to be in some sort of spectrum-like units. For examples today, these will all be in microjanskis, or at least this notebook is all microjanskis, but it'll be perfectly happy to be lambda style units or even photons, or magnitudes are even supported if you really want to represent your spectra that way. Spectrum 1D objects can also store a few other things. Most relevant for this are uncertainties. We'll get to that near the end of this notebook, which basically are the same shape as the flux, but are the uncertainties associated with it rather than the flux itself. And then the WCS, right? So the WCS is a somewhat subtle thing. It's a piece of information that tells you how to map from pixel coordinates to world coordinates, which in this case means the spectral axis. And I'll show you an example of how that's useful in just a minute, but the key point is it's sort of derived from or intertwined with the spectral axis. So all that might seem a little abstract. That's okay. The first thing we're going to do is make this a little bit more concrete. as I said, there's other ways of representing spectra if you don't have just simple one-dimensional spectra like I'm talking about. But if that's the case, they're sort of logical extensions of the Spectrum 1D, so you'll want to look in the documentation or ask questions in Slack later, and we can talk about that. Instead, we're going to jump into the sort of basic things you can do with a Spectrum 1D object. So we're going to start by loading a spectrum from an example JWST data set that we've prepared for basically for the purposes of this webinar and similar activities. So there's this magic URL here that maybe is a bit opaque, but the key point is you'll have to just trust me that it's a spectrum that's JWST simulated data. So this is just some URL. We're going to have to download that somehow. So what we're going to do here is import tils. We're going to import a data downloading function. And we're going to download that file right into the location that this this platform runs in. So I've typed all that out. Now I'm going to type Shift-Enter. It executes and happened really quickly and downloaded. Do this just so it doesn't have to run a second time later. This caches it so that it doesn't download it every time, only once. And that downloads the file to some magic location that, in fact, you don't really care that much about other than that it's a file somewhere on the platform. What I'm doing right now to get new empty cells to work in is I can select a cell and hit, say, the B key to make a new cell below, or the A key to make another cell above. That's a good way to get extra cells if you want to do some experimentation. But once we've got this file downloaded, we can now load it into a Spectrum 1D object. And the simplest way to do this is sort of stunningly straightforward. All we do is type spectrum1d.read. That's a function, a class method, but basically a function that you pass in the name of the file. We execute this cell, and it executed just fine and printed out a spectrum. Right? This is flux and spectral axis. So in many cases, this is essentially all you'll need to know about, especially for JWST, where we're taking active effort to support all the data types you'll download. All you need to do is do spectrum1d.read. So to see all of the things that are available for reading, you can do this help on the spectrum1d.read. It prints out the help, and you can see there's a whole bunch of formats here, some of which are JWST formats, and some of which are lots of other things like the Sloan Digital Sky Survey, Manga, Apogee, all kinds of different sort of spectroscopic surveys. And these are all been contributed by other surveys and team members. But the main point is that most of the JWST data is included here, right? So in many cases, you're just going to be able to do that. That said, to understand what's going on with Spectrum 1D and be able to use it effectively, it's useful to see how these readers map onto the sort of more manual way of building a spectrum. So we're going to take a minute to try to reproduce exactly what that read function did, but by hand. Need a few cells to do that. We're going to do that by using the astropy.io.fits module, which is a way to load fits files. That's sort of a lower level way of loading fits files that doesn't automatically turn them into spectrum or spectra. And we're going to look at what this file is that we just were loading before into Spectrum 1D. So the file we had just loaded a moment ago using spectrum1d.read is this is really a quite simple looking file. It's a very basic table fits file with just one HDU that's a table HDU. That's 3,000 pixels long and two pixels or 2 columns wide. Let's see here. And this file Oh, by the way, what I'm doing right now, in case you don't know this trick, if I start typing something that's I can, and then hit tab, it will autocomplete, right? So that's a fast way to sort of type faster in the notebook. And if there's multiple options, it'll show you this menu and you can choose the one you want. So I'm using the arrow keys right now. I choose fits file, it autocompletes. But I want to look at the HDU number 1 there. Look at its header. If I do that, I see that these two columns are a wavelength column in microns, a flux column in microjanskis, which if you were paying close attention above, you might have noticed that's exactly what we were getting here, microjanskis and microns. So this is though just enough information to build the Spectrum 1D object. So we know we need flux column. So we pull out, first I have to make a convenience variable with the data itself. If I just execute that, you'll see it's a fits table, which it turns out is pretty straightforward to access by just doing stuff like that. Like a Python dictionary is essentially what that style of access. But to make now a Spectrum 1D object, I do that by doing something like this, and then assigning it a unit by multiplying it by one of these unit objects. So, sorry, cursor's in the way. I'll do the same thing for the spectral axis. Table data of wavelength, it's called in the table. You know that's in microns, because that's what it says right up here, so I can assign it units that way. And then to create the Spectrum 1D object by hand, I do Spectrum 1D, and then flux equals that flux object I had up here. Spectral axis equals the same thing I had right up here. So that should yield the same kind of object. Good. So now we can actually look at the spectrum, which should be the exact same between these two cases. Do like spectral axis versus flux. And if I do that, I see a plot that looks like a spectrum, like a sort of classic galaxy spectrum. And if I do a very similar thing, but using the original spectrum I was looking at before, we call it JWST spec, we can see we get out the exact same spectrum. So this was the same thing. This is basically our little by hand implementation of what spectrum1d.read did. So next thing I'm going to talk about is some of these attributes that Spectrum 1D objects have on them, and what we can do with them. So let's start with the spectral axis object. So we've been using this already, but now that we show it, you see that it's basically an array with associated units, right? So it's an AstroPi quantity object. So let's just say a few more things. On its own, that might not seem particularly useful, but the main reason why it's useful is because it lets you do some handy things with unit conversions. For example, if you want to convert to angstroms and you don't remember, is it 10,000 or is it 1,000? What is it again? You can just do that. And it did the correct conversion, trust me, if you don't remember. That might seem a little silly in the case of angstroms, but the place where it starts making more sense is when you have to try to remember all those spectral conversions that, if you're like me, just leave your head as soon as you do the homework problem in grad school. For example, suppose you want to convert to terahertz, right, from wavelength to frequency. You can just do this directly by telling, so I should highlight, what you cannot do is do a conversion to, like, I don't know, Janskis, right? A spectral axis, microns cannot be converted to Janskis because those are not at all similar units. They're completely different kinds of units. So if you do that, it'll give you this unit conversion error. But if you want to tell it, hi, I'm actually working on a spectrum computer, trust me. You can give it this thing called an equivalency that really you don't have to understand beyond if you do u.spectral, just like I did here, and then execute this conversion. It knows this is a spectrum, and that since it's a spectrum, I know how to turn microns into frequencies, and I won't give you this error because it's a spectrum, so it's okay. So that's a less trivial conversion than the one we were doing before. You can even do even more convoluted ones, like, if you work in EV, if this is like an X-ray spectrum or something, you can do that, and it's remembering all the conversions for you, so you don't have to remember where the factors of C go and all that stuff. Now it might seem a little silly. You have to say spectral when it's actually from a spectrum. It turns out there are useful little accessors in Specutils to make this easier in the Spectrum1D object. Instead of doing spectral access, you can just type JWST spec.frequency, and that did the conversion to frequency for you without having to remember this 2 and the spectral business. So that's convenient. That's an example of the sort of thing that happens, and it lets you, for example, combine the various conversions and steps we've been doing together to do something like this. Case S. And now you can see when I do this plot, it's the same spectrum, but it's going the other way because frequency conversions, of course, flip the direction of the spectrum. All right. So then another thing to keep in mind, a thing that I mentioned before when I was talking about the information that's stored in Spectrum1D, is that not only is the spectral axis available as just an array, but it can also be a WCS, a world coordinate system. So if you want to do things like ask, where is pixel number 10? Okay, that might seem silly because that's one of the pixels that's already on there. But advantage of this is I can also say pixel 10.5, which of course will not appear in the array because it's in between pixels, but this pixel to world conversion will perfectly happily do that for you. And perhaps even more useful is that this machinery will also do the other direction, right? World to pixel. I can say, can you tell me where 1 or say 2 microns are? I have to specify a unit now because it's a world coordinate that actually has associated units. But what do I do? Oh, I think it has to be. I think those aren't in the spectrum. There we go. Yes, that was off the edge of the spectrum. 1.2 and 1.3 microns is a more reasonable thing to ask for. And you can see there now it gave me back pixel 850 point something and 1276 point something. Right, so not only are these just arrays you can work with for plotting purposes like I'm showing before and to convert, you can also use it to do these sort of interpixel conversions. And that all works sort of the way that naively you would expect it to do so, even though you might have only given it an array at the beginning. The other thing that's useful about these objects is we can do similar sorts of things in flux realm, right? So for example, the flux is this microjansky object, which is astropy quantity, just like the spectral axis was. But it's in flux where you really, if you're like me, you spend some time getting confused about what the right spectral units are. For example, if I want to convert from Janskys, which are F nu units, to F lambda units, you can define your favorite representation of F lambda units. This is the way I learned on the knee of my advisor, is what F lambda units are. Looks like that, right? Ergs per second, per centimeter squared, per whatever microns in this case the spectrum is. And to do that conversion, again, it's just go to those units. But now instead of telling it it's spectral, I have to tell it it's a spectral density, because that's a slightly different thing. And as an extra bit, I have to tell it where in the spectrum I am. Right? So this magic incantation now converted the flux axis from the F nu units of microjanskys to F lambda units of the kind I'm showing you here. That might be the sort of thing where you're like, I could never remember all those random things I have to type without copying and pasting. Well, the good news is you can do lots of copying and pasting. That's why we're giving you these materials. But on top of that, you still don't have to remember, because Spectrum 1D has little accessors to make life easier in this respect as well. There's something called new flux unit that we can give it f lambda units, and it will yield a new Spectrum 1D object that is in the units we wanted. So for example, we can call it this because we're going to use it more in a little while. That's the exact same thing I was showing you before. And if I plot that up, spectral axis versus flux, you see that not only is it in f lambda units now in just the unit conversion, it's also correctly done the thing of resloping the spectrum, just like it's supposed to. Again, if you're like me, you always forget whether you're supposed to divide by or multiply by, but I didn't have to remember. The computer remembered it for me. And let's be honest, you would have just Googled it anyway, right? So might as well have the computer do it for you the other way. So that's the accessors of all the pieces of Spectrum 1D, and sort of demonstrates for you the point of using Spectrum 1D as a way to carry stuff around and help you remember things that you either can try to remember or you can forget about and focus instead on your science. The other thing I wanted to show you here is arithmetic operations, to show how you can sort of do straightforward operations on the spectra by just doing things like subtracting and addition, or subtraction and addition. So for example, if we look at this spectrum, actually let's look at the original version of it up here. Just going to plot it down here so that we can refer to it. When we look at this plot, we can see it actually goes to like 0.5, right? There's clearly a continuum in this spectrum. So let's do the cheapest and easiest version of continuum subtraction possible, of just subtracting off the sort of by eye lowest continuum level of 0.5 microjanskis. I can do what seems fairly sensible. Take the spectrum, subtract off 0.5 microjanskis. And if I do that, plot the thing up, spec1d dot spectral axis, spec1d dot flux, and it looks exactly the same, except the continuum level is at 0 instead of 0.5 like it was up here. So even though this warning that might look scary showed up, that's nothing to worry about. It successfully did what you expect of just subtracting off this value. Now, this is great for situations like this where it's clear what you're trying to do. There is a gotcha to worry about here, though. You might think, oh, I can use that to subtract off my other spectrum, the one that I had in f lambda units. That might seem unambiguous. The problem is, it is ambiguous because the computer doesn't know whether you wanted to return it in f nu or f lambda units. So following one of the principles of Python to refuse the temptation to guess, it says, I don't know what to do. These dimensions don't match. You have to decide what you want to do. So you as the user can just say, okay, I know what I want to do. I actually meant it to all be in f lambda units, so I can do that. Subtract off the spectrum that was already in lambda units. And I get out something now that it happily did. It subtracted one spectrum from another, and it gave me back a thing that is essentially all zeros, or very close to 0, because I subtracted something from itself. So that's a key thing to keep in mind, that although these arithmetic operations are generally very straightforward and natural arithmetic operations, you do have to be aware that the units have to match. The last thing I want to talk about is how you add uncertainties. Right? So we had a question earlier about loading uncertainties. Some files will have it built in, but oftentimes we don't have uncertainties and we have to infer them somehow. So I'm going to do the simplest approach to this. So let's think about why we would want uncertainties. One of the easiest reasons is because we want to compute the signal-noise ratio of our spectrum. We have the signal, that's the flux, but we need a noise. It turns out the simplest way to do this sort of thing, that's often the case with Specutils, is that you can find some function that does some reasonable guesses for you. There's already a function defined in Specutils.analysis called SNR derived that does sort of a back of the envelope guess for what the a sort of standard algorithm that's defined in the literature about guessing what the noise level should be, and then computes a signal noise for you, and will just give you an answer. So you could always do that if you want to, but for some cases, for example, JWST data will have more information about the uncertainty, so you also want to figure out how to actually roll the uncertainty in. So in the case of the spectrum we've been looking at before, you can kind of look by eye and see that there's what the noise level is. We'll see some example, or there are other ways you could do this, but for the purposes of this webinar, we're just going to by eye guess what the level of the noise is, and conclude that it's something like 0.05 or so microjanskis, or noise level 5, let's say. Now to include uncertainties in this object, we have to do one step more complicated. We have to tell what kind of uncertainty it is, right? As somebody asked in the Slack a little while ago, some people will tell you the right way to do uncertainties is inverse variance, and others will say the best way is, variance, and others will say it's standard deviation style uncertainties. So you have to tell Spectrum 1D that which kind you want. In this case, we're just going to say, because we eyeballed it, standard deviation style uncertainties. We create an uncertainty object that uses this standard dev uncertainty. It's at our noise level, and it has to be of a size to match the spectrum. I'm using this ones-like function from NumPy that just says, take the flux and give me out a new array that's just like that, but with values of 1, which we then multiply by our common noise value. So, you could do something more complicated if you wanted to, if you had some other way to derive this from your data, but for now we're just going to say it's a flat noise level. Then we can make a new Spectrum 1D that we make from the old one by saying spectral axis equals the old one's spectral axis. We don't want to touch that. Its flux equals the old one's flux. But the uncertainty is now going to be this uncertainty object we just created right up here. And then now we're going to plot that with its uncertainty. This is just sort of a quick and easy way of plotting something's uncertainty, where we plot the spectral axis against the flux plus the starts with minus the uncertainty t, and then uncertainty, got it, and then plus. Make that plot. We'll see if I didn't misspell something, which apparently I did. Oh, right. And you have to do an explicit conversion for reasons that we won't dwell on right now for the sake of time. But when we do this plot, now we see that it's captured the uncertainty as sort of a faded region there. So after that, now we can successfully use the signal and noise function to compute the signal and noise, and we get a different answer because we had quite different assumptions than this sort of back of the envelope does here, because our calculation is aware of the fact that the spectral lines, the emission lines, are not part of the continuum essentially. So, or at least maybe I shouldn't say are aware of. It's a different set of assumptions is the key point. And for any given data set, that's going to give you a better answer.